Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 12-4 Part 2 homework solutions. This one dealing with inverses of matrices and using them to solve systems of equations. For this problem, they want us to use technology to find the inverse of this matrix and then verify the result. So let's go ahead and just plug this in Desmos, the matrix version of the calculator. Just move over here so I can see. So I will make a new matrix, and I'll make it 3 rows and 3 columns and just enter what we've got here. So we've got 1, -1, -2, 0, 1, 2, 3, 0, and 1. And now I'll just come down to a new entry here, and we'll do a and then exponent -1 to get the inverse, and here's our inverse. 1, 1, 0, 6, 7, -2, -3, -3, and 1. All of that stuff. Now to verify it, we just need to make sure that when I multiply these together in both directions, I get the identity matrix. So let me go ahead and check that. So we've got A inverse times A comes out to the identity matrix. We've got the diagonal ones and the zeros. And if I put this A before A inverse and do the opposite direction, we also get the identity matrix. So this verifies that this is indeed the inverse. In the inverse of this matrix using technology, we're going to use the Desmos matrix calculator. Our first step on here is going to be to make a new matrix and make it a 3 by 3 using this little row adjustment deal. Let's just enter what we've got here. So 2, 1, 0, -3, 4, 7, and 5, 0, -3. And then let's come down to a new entry level, and we'll just do A and -1 exponent. So we got A, exponent, -1, and this is a little bit crazy. We've got -6 and 1.5, 3.5, 13, -3, -7, -10, 2.5, and 5.5. And if you like, you can turn all of those into fractions. So 3 halves, 7 halves, all of those. So put it in whatever format you want, fraction or decimal. Either way, we need to verify that this is the inverse. So to do that, we're going to do A inverse times A to see if it gives us the identity. And looking here, we've got the ones and zeros, so that is the identity. We also need to do A times A inverse, both directions, because it could be different. And we get the identity there as well. So because A and A inverse in either direction of multiplication give us the identity, A inverse here is truly the inverse. To solve this system using an inverse matrix, we're going to set up an equation with AX equals B sort of thing. The A matrix is just the coefficient matrix, and we'll put these constants in a B matrix on the other side. So on the left side of the equation, I've got a matrix with 1, 2, 3, and 7. And we're going to have an X, and we're going to have an equals another matrix with a 1 and a 2 in it. So now I just have to solve this matrix equation in order to figure out X and Y. To do that, I'm going to need to find the inverse of this A matrix over here and multiply that by both sides of the equation. So inverse of this matrix, we're going to do the determinant, or 1 over the determinant rather. So we've got 7 minus 6 for that. And then we're going to switch the A and the D, so that becomes a 7 and a 1. And negate the 2 and the 3, so -2, -3. 7 minus 6 is just 1. So this, just the matrix part of here, is actually our whole inverse matrix. So we're going to multiply this now by both sides of this matrix equation that we set up. So we've got the matrix on the left side, which is going to end up canceling out this original matrix, leaving us with just X. And we've also got this matrix to the left of the matrix on the right side. We have to do it left times right. If you try the other direction, I think it would just give you an error, because you'd have a different number of columns versus rows. So multiplying this out matrix style, we do each row times this one column. So we have 7 times 1 plus -2 times 2. That's 7 and -4, giving us 3. And now we do the bottom row times the column. So -3 times 1 plus 1 times 2. -3 plus 2 is -1. So then this gives us the answer of 3 comma negative 1. To solve this linear system using an inverse matrix, let's start by setting up a matrix equation. So we'll have a matrix on the left side of our equation that has the coefficients, and then we'll have an x that we're solving for, and a matrix on the right side of the equation with the constants. So on the left side, I've got -7, 2, 5, and -3. And there will be an x that goes over there with it. And on the right side, we're going to have an equals matrix with a 29 and a -27. So just a 2 by 1 matrix there. So to solve this matrix equation, which will solve the system of equations, we need to find the inverse of this left matrix. So we'll do 1 over the determinant. So that's 1 over, let's see, this will be 21 minus 10. And for the matrix part, we're going to switch the a and the d. So -3 versus -7. And then we'll also negate the b and the c. So -2 and -5. So I'm going to refine this a little bit more, and I'm going to multiply it by the left and the right side of this matrix equation. So we've got, this is going to be 1 over 11 when the dust settles. So this -3 becomes -3 over 11, because we're going to distribute this to each item in the matrix. -2 becomes -2 over 11. -5 is -5 over 11. And you guessed it, -7 over 11. So we're going to multiply this by the left side, which is actually going to cancel out these matrices because they're inverses, leaving us with just x. We'll also multiply it by just these 2 items on the right side, but we need to put the inverse on the left of that right side matrix in order for this multiplication to work. So multiplying this out, this is going to be a little bit weird. We're going to do each row times this one column. So we've got, let's see, I'm just going to do this on the Desmos calculator. We can just use the scientific calculator. I don't need a matrix calculator for this, but I do need a little bit of number crunching help. So we got -3 over 11 times 29 minus or plus -2 over 11 times -27. So that comes out to -3. That's our top answer there. And now I'm going to do the bottom row times the 29 and the -27. So I'm just going to replace this first fraction with 5 over 11. And this second fraction is now -7 over 11. And that all comes out to 4. So final answer, we've got -3, 4. In order to solve this linear system with an inverse matrix, we're going to set up a matrix equation. So we're going to have a matrix with my coefficients, an x, and that's going to equal a matrix that has my constants in it. So for my coefficient matrix, we've got 3, 1, -1, and 2. I've got an x, and then I've got that equaling -1 and 12 in its own little matrix. So to solve this, I need to find the inverse of this left side matrix. So that's going to be 1 over the determinant of this thing. That's going to be, let's see here, we got 6 minus -1, so 6 plus 1 down there. And now for the matrix itself, we need to do A and D switching, so 2 and then 3. And then negate these 1s. So up here is a -1, down here is now a +1. And then this will end up being 1 over 7 times all of these things. So we're going to end up with 1/7 times 2, so 2 over 7. And I'll start multiplying this inverse matrix by each side of the equation while I'm constructing it here. Then we've got -1 over 7, 1 over 7, and 3 over 7. And I'll also multiply this by the right side of the equation. Now for the left side, since these are inverses, this just gives me the identity matrix, which just cancels out basically, because when you multiply the identity by whatever this x matrix is, you just get the x. So now I just have to really multiply these ones on the right here. Let me use a Desmos calculator to help me do this, just for the number crunching. I don't need the matrix part of the calculator, just the scientific part. So we have to do each of these rows by this column. So we've got 2 divided by 7 times -1. Let's see, minus or plus -1 over 7. times that 12 down here. And if you can believe it, that comes out to exactly -2. All right, well, we'll take their word for it. And now let me switch this up. I need to do my bottom row times -1 over 12. So for now, instead of the 2/7, I've got a 1/7. That's all I need to change there. And instead of -1/7, I now have plus 3 over 7 times 12. And that all comes out to a result of 5. So our final answer then is the point -2, 5. For this problem, they want us to use an inverse matrix and technology to solve this linear system. So to do that, we need to set up an A and a B matrix and then solve a matrix equation. So my A matrix is just going to be my coefficients of all this. So that's -3, 1, -8, 1, -2, 1, 2, -2, and 5. So all of these coefficients just in matrix form. For my B matrix, I'll just take the constants on the right side. So 18, -11, and -17. So we're going to be solving the equation AX equals B, just like we would do for a 2x2 system of equations. So to solve this, we essentially need to find A inverse and multiply it by both sides. That'll cancel out the A on the left side, leaving us with X equals whatever A inverse times B is. So we're going to do the rest of this on the calculator. So here's Desmos. Let me set up two matrices. My first will be a 3x3 for the A matrix. So that's -3, 1, -8, 1, -2, 1, 2, -2, and 5. And let me set up another matrix. This will be the B matrix, which is a 3x1. So I'll adjust those rows and columns a little bit. And I'll put in an 18, -11, and a -17. And all I need to do at this point is really just A inverse times B. So A, exponent, -1, go down to non-exponent level, write B, and instantly we get the matrix -2, 4, -1. This means that my final answer is going to be -2, 4, -1. For this problem, they're giving us some information about how different combinations of flowers, how much different combinations cost. And based on all this, they want to know the cost of each type of flower. So what we're going to do is set up a system of equations with all of these in it, and then we'll solve that. So just for simplicity's sake, I'm going to let the cost of a rose be represented by R. We'll let C be the cost of a carnation, and T will be the cost of a tulip. So for this first piece of information, we've got 2 roses plus 6 carnations plus 2 tulips, all costing $23, so equals 23. And that is one of the 3 equations then that we're going to use. For the next sentence, we've got 4 roses plus 4 carnations plus 2 tulips equals 30. And then lastly, 3 roses plus 2 carnations plus 5T for tulips equals 28. So there is our 3x3 system that we're going to solve. Since we're going to be solving it with a calculator, we have to set up a coefficient matrix and a constant matrix, and then basically just do A inverse times B. So let's set up our coefficient matrix first. We're going to have 2, 6, 2, 4, 4, 2, and 3, 2, 5. So all of the coefficients on the left side go in this A matrix. And then for our B matrix, we'll have our constants 23, 30, and 28. So we're trying to solve the equation A times X, and X is our solution matrix, equals B. To do that, we just need to find A inverse and multiply that by both sides of this equation. That's going to cancel out the A matrix, leaving us with just X equals, and then whatever A inverse times B is. So let's go to the Desmos matrix calculator. Here we are, and I'm going to make a new matrix, 3x3, that has my coefficients in it. So 2, 6, 2, 4, 4, 2, 3, 2, 5, and then we'll make another matrix that has 3 rows and 1 column, to house my B values here. So 23, 30, and 28. And then we just go down to another entry, and we just have to do A inverse, and then multiply that by B. And that gives us 5, 1.5, and 2. So 5, 1.5, or 3 halves, and 2. So what does that actually tell us? Well, this top value here, the way that we set up our equations, R was the first thing, C was the second thing, and T was the third thing. So this top value is the cost of a rose. That is going to be $5. Wow. And then we've got 1.5. That's the cost of a carnation. That's $1.50. And then finally, tulips are going to be $2 a piece.